So this is the setup for this experiment. So we have three-phase transformer here, we have loads. In here we have either we can use a resistive load or a reactive load. For this experiment we're going to use resistive load. And if you look at the transformer section, we have three-phase transformer, but since this experiment requires single phase, we're going to use one of them. And this is the power supply unit that we are going to use, since we need variable power supply. So we are going to use this variable power DC voltage source. So we are going to use either one of them, A or B or C, and a neutral to have a three-phase connection. So I will explain everything. So let's go to the transformer section. There are two segments, where in one segment we have primary side. It starts from H1 to H5. So there are two windings, two separate windings. H1 and H3 is one winding, and we tapped out from H1 to actually form H2. As I've mentioned earlier in my previous video, so we can actually tap out from any point, because if we need a certain number of turns, we can tap out from any position. Like, say for example, if this is a transformer, so there are so many cables coming out from the winding, so we can actually tap out from any turn and make it use as a output or input. So we can use it like this. So there are two windings on the primary side. So if we want to actually use the whole thing, we need to actually connect them. So these two. So this is the first section of the winding, and this is the second section of the winding. So but if it requires, like for instance in this experiment we're going to use all of them, so we need to actually connect these two, H3 and H4, in order to have a larger number of turns. So same goes for the secondary side. Although there are so many taps, but basically it also has two large windings. One starts from X1 till X4, and this is X5, and X7 is a separate one. So there are taps coming from X1 and X4. There are two taps, and one tap is coming from X5, X6, X7. So these are the names actually. So for the experiment we're going to use some banana cables like this to join, like for instance from this point to this point we're going to use smaller banana cables, and larger banana cables like this we're going to use them to connect the power to the primary side, and from primary side to the load. So let me bring also like the power analyzer that we're going to use. Say for example, I showed you earlier, so we are going to use something like this type of power analyzer for measuring current and voltage. But without the power analyzer, let's have the circuit done, then we'll include that one. Okay, if you want to include the power supply to the primary side, so let's use one of the banana cables. I'm not gonna bother about the color coding for the time being, because it's all AC, so there is no positive and negative, and it's only a single phase connection. So what I'm doing right now, I'm actually connecting A phase to one of the points of the transformer, and the neutral to another point of the transformer, so another lead. So from A it goes to H1, from neutral it is going to H5. So it is supplying to all the windings of the primary side. So it is energizing, it is supplying voltage from H1 to H5, since we have connection from H3 to H4. So if we remove it, even if we supply voltage, it will do nothing. There will be some voltage but there won't be any current circulating. So we need to have this in order to short circuit it. Anyway, so again for the secondary side we need a short banana cable like this. We're gonna connect this to this jack, and we'll connect the secondaries X1 to X7, that means the whole winding, to the load, one of the loads. Like we could use A, B or C. I choose to use B. So we can change the value of resistance like this, or we can use one of them. Okay, so that's all for the connection. Now we need to actually incorporate the, what is it called, the power analyzer in the circuit. So in order to do that, we could have actually used the ammeter and voltmeter, but it's for me it's easier to actually measure all of them together, like for instance the voltage, current, power factor. So that's why we're going to use power analyzer in this case. So that's the power analyzer. If we want to connect the power analyzer, we need to get rid of all the connections. So let's open the power analyzer here. We're gonna connect the power supply to the power analyzer like so. There are, in the power analyzer you will see there are four sets of jacks. This is the input, these two are for input and these two are for output load. So we're going to connect the inputs to the power supply to the input, and this output will go to the primary side. So whatever the current is going through it, it will measure. Whatever the voltage is supplying from the power supply, it will measure. So there are four sections. We can measure not only like the voltage and current, we can measure power factor and watt. So let's connect it. So the output of the power analyzer will directly go to the primary of the transformer. And for this experiment we'll need another power analyzer, since we're that one is for the primary side. For secondary we also need a power analyzer, which will be here. Let me connect it here. So from the secondary, since this is one of the first experiments that we are doing together, so that's why I'm actually showing you everything. But for next experiment I'll actually connect it before recording. Anyway, so this is the output of the transformer, or the secondary of the transformer. It will go to the input of this power analyzer, and the output of the power analyzer will go to the load. Okay. Okay, that's all. I know it's a bit like messy, but we need wire to connect, right? But one more thing, we also need to actually power the power analyzer, because it requires DC voltage of 12 volts. So we use these sorts of power adapters. So we are gonna use it to actually power the power analyzer measurement unit. So that's that. Let's connect it. If we turn this on and switch it on, you will see I can actually this machine is on. Okay, I need another adapter for the second one. So that's that. Let me clear everything. Okay, so first thing is first, we will turn on the main AC. So after turning on, I am going to turn on the power analyzer. So I'm turning on power analyzer 1 and I'm turning on power analyzer 2 right now, and I will switch this off to energize the auto transformer here, because we are gonna use it for variable power supply. Okay, so the dial is at 0, so if you look at the primary side, the voltage is 0. So if I increase the dial, the voltage will go up. Like, let's say for example I want to supply 50 volts AC. So see, from here there are reflections, I know. Okay, so you can see the voltage is 45. Let's bring it up a little. So that's 50. Yeah, that is 50 volts, so approximately 51. So if we look at the secondary side's measurement, so it is 25.2. It means that this transformer, this setup is a step down transformer. So primary is winding and secondary is windings turns ratio, if we ratio them, it'll be, transfer ratio would be like half, since it is actually a step down transformer. If you look at the current, so the input side's current is 0.036 and the output side's current is 0.058. It is approximately doubled. So because there are some losses in the system, so that's why it is not exactly double, but there are some losses in the cable, there are some losses in the transformer's winding, there are some losses in the resistive load. So if we consider all of these losses, and there are some losses in transformer cores as well. So I hope you already, I know that you already know those theoretical things, because in this lab that is very important to know all of this. So those are the reasons that we didn't get exactly the amount we are supposed to get, but we get the point. So now if I increase the amount of voltage, like from 50 to 120, so yeah, that's 120. Yeah, 120. Okay, so if you look at the secondary voltage, it's not exactly 60, but it is 59.3. So because there are some losses, this is not an ideal case, this is a practical case. And if you look at the current, which is 0.083, whereas here the current is 0.143. It's supposed to be 0.16, but it is not, because I told you there are some losses in the system. So that's all for today. So this is the transformers transformation ratio calculation. So I'd like you to actually have these readings that I'm gonna show you right now, and make a table and do some calculations that I have mentioned in my previous video, and write a report on it. So the reports, the instruction for the report will be given to that video. From that video you can get the idea how to do the report writing. So okay, with 120 volt the supply voltage, if the supply voltage is 120, if you look at this is 120.4, the current is 0.083, and the power factor here is 0.69, and the power for the primary side it is 9.6. I'm sorry. And for the secondary side, the power is 9.2, power factor is 1 because we have a resistive load, and voltage is 59.3, and the current is 0.143. So I'm gonna increase the voltage, and you're gonna I'd like you to actually record those. So I'll increase the voltage to 140 volts. Okay, so I'd like you to take reading. So primary side's power is 13.1, power factor is 0.97, voltage supplied voltage is 40.6, and the current is 0.096. On the secondary side, the power is 12.2. There are some losses, significant amount, 1 watt loss in the system. So it could be in the core, it could be from the winding itself. Power factor for the secondary is 0.1, not point, so it's an unity power factor, which means 1, and the voltage is 69.5, and the current is 1.68. So there are I have given you 2 sets of values. I'd like you to calculate and include them in the report. Thank you.